Okay, hello, thanks for coming back. Let me go ahead with a third lecture on string amplitudes. To connect with what you have seen last time, we finished off the introduction to tree amplitudes in the RNS formalism. We took a first look into the pure Spinor formalism. I wrote down the worldsheet action, the matter sector and the ghost sector. I gave you some evidence that it's a well-balanced system, that matter and ghosts work well together to get a vanishing central charge and to get the Lorentz current algebra with the correct level to reproduce the OPEs of the RNS formalism when you look at the Lorentz currents from there. Yeah, the ingredients from yesterday that we massively will need today, one of them is about the OPEs of various conformal fields. Just to remind you, this field pi is essentially del x plus a correction term to make it space-time supersymmetric. And this d alpha, it's essentially the p alpha variable, the momentum conjugate to theta. And again, it has a supersymmetric completion. So d alpha and pi are, if you wish, the good variables that we will also use in the vertex operators. Okay, so here you see a collection of OPEs from the matter and the ghost sector. And there's one buzzword that I forgot to mention yesterday. What I was describing to you is the so-called minimal pure Spinor formalism. As the word already suggests, there also exists a non-minimal version with slightly more variables. But this non-minimal formalism is extremely useful when it comes to computing loop amplitudes. It allows you to do precision calculations, including the global normalization, which in turn is important to match with the predictions of S-duality. So if you want to read about the non-minimal version, you can, for instance, look at this paper. This is where the non-minimal pure Spinor formalism is introduced. Good. Yeah, so strictly speaking, these OPEs are all you need to know, but to give some additional service, you will later on have a situation where we need to evaluate OPEs on a superfield. To take the surprise ahead, the vertex operators will contain superfields that are functions of x and theta. And first of all, when I say superfield, I have in mind that they don't depend on the worldsheet derivatives of x and theta. And to be super careful, from the worldsheet perspective, a superfield means it's a function of x and theta, where x and theta in turn are functions on the worldsheet. I hope this bracketing here doesn't make you nervous. So let's not forget that the arguments x and theta of the superfield are by themselves functions on the surface. Okay, and if you put the OPEs from above together, what you find is the OPE of pi and the alpha with a superfield. In both cases, you get a simple pole, and the residue is either the space-time derivative of the superfield or the fermionic covariant derivative, which is defined as here. And in a second, you will see these OPEs applied to the fields of 10-dimensional super Young-Mills. So I was introducing the theory yesterday by showing you the minimal input, how you can put that theory on shell. You impose a certain anti-commutation relation among connections that are UN valued. And I use this funny double dash notation here for the superfields of the full nonlinear theory. As you know it from pure Young-Mills, the Lagrangian F mu has a lot of nonlinearities. This is where the interactions come from. So here are the analogous nonlinearities in the equations of motion of 10-dimensional super Young-Mills. Apart from the potentials A alpha and AM, there are some gauge covariant field strengths in here. So this field strength F Mn is analogous to pure Young-Mills. It's basically a commutator of bosonic covariant derivatives. And here, this W, it's a fermionic analog of a field strength. It's something like a curl mixing a bosonic direction and a fermionic direction in the superspace. Okay, so this is the full nonlinear story. But for most of what you see today, you can skip these terms. So the linearized version of this theory is, by definition, not having these terms. Okay, so for the purpose of getting vertex operators, all we need to worry about is the linearized version of that. And the notation for the linearized discussion is that you just omit the double dashes. So whenever I refer to solutions of linearized equations of motion, then I use the symbols you're seeing here. Oh yeah, let's write it here. So Fmn is up to a minus sign. And this connection in turn is defined as that one. And analogous definitions hold when you replace one of the vector indices by alpha. Then fermionic connection is d alpha, this d alpha, minus an a alpha spinorial potential. And analogously, right. Exactly. So when you linearize, then all you keep is this partial. Okay. Yeah, please interrupt me if something calls for further explanation.
Looking at that perspective would be more, in certain sense, natural to change the Spinor derivative d alpha to include also the super gauge potential a alpha, because you could move everything inside.
Sorry, which?
You can reabsorb a alpha, the non-linear term,
Yeah.
into d alpha.
Ah, yeah, right. Yes. Okay, that's true. Yeah, I chose to write it in this way because we will later on use the d alphas acting here. But okay, strictly speaking, it doesn't really matter. I could have equivalently told you to, yeah. And even later today, you will see an example where this shows up in the OPEs. But okay, I hope it will make sense in the way as it is written now. Where was I? Yes, was about to tell you something about the linearized versions of all these superfields. So if you throw away the nonlinearities in the equations of motion, you have a much simpler scenario. And let's now do a degree of freedom counting for the solutions to the linearized equations of motion. So the claim about these linearized superfields is that they contain 8 plus 8 on-shell degrees of freedom after taking the gauge freedom into account. You were yesterday seeing the nonlinear version of that, but at the linearized level, the gauge freedom in A alpha and AM is that you can shift the two by some derivatives of scalar quantities. So this is just a shift of AM by a gradient, as you know it from Maxwell electrodynamics already. And that equation here is just a continuation into the fermionic directions. Okay, so this is the linearized gauge freedom that you have to subtract in your mind when you count the number of on-shell degrees of freedom. Okay, and if you now look at which kinds of bosonic components and fermionic components do I need to specify, you will see on the bosonic side there is a vector that counts degrees of freedom, a vector with gauge redundancy inherited from here, but you need to make sure that this vector is transversal. Okay, and so these are precisely the conditions that you're used to from counting degrees of freedom in a gluon. But from all the spinors in the game, there will also be degrees of freedom associated with spinorial wave functions. And here you need to make sure that the massless Dirac equation holds, that these chi's are annihilated like that. So this is the gluino. Okay, so far this is a claim. Let me give you some idea of how to arrive at this result. And let's make use of this gauge freedom to maximally expose the degrees of freedom. So there is a convenient gauge. I think yesterday it was asked whether there's an analog of Wess-Zumino gauge that is quite popular in 4 dimensions. And yes, there is. So for 10 dimensions, it's convenient to go into Harnad-Schneider gauge, which is defined by imposing this contraction, theta alpha into A alpha. We want this to vanish. And you can always attain that. Suppose you start with an A alpha where this doesn't vanish. Then you can add some D alpha of omega. You can always find a scalar omega such that you enforce this. Okay? And in that Harnad-Schneider gauge, we can be pretty explicit about the theta expansion. So the theta expansions in Harnad-Schneider gauge are displayed right here. The consequence of this theta alpha A alpha equals 0, you won't have a 0th order in theta for the spinor potential, and all the remaining entries are fixed by the 0th components of the later fields. So when you just look at the first line, you will see some a priori undetermined vector, but later on you will see, okay, this is the vector that appears in the 0th order in theta in the next superfield. I mean, all of these 4 superfields on that blackboard are entangled through their equations of motion, here the linearized ones. And in Harnad-Schneider gauge, it's precisely this theta expansion that will solve the linearized equation of motion. Oh yes, right. This deserves a disclaimer. As you can imagine, there will be plenty of momenta in the subsequent formula. So if you want to roll back to the conventions used until yesterday, you need to send k to ik to match. So when we are done with the pure spinor chapter of this lecture, I will roll back to the more usual conventions. It's just for convenience that I don't have to think about plus minus I in various intermediate steps. There are many formula where you will see that it's a headache to have these factors of I. Oh, absolutely. You can. Sure, just contract this equation with the corresponding gamma matrix. Right, that's a very important remark. You can solve, the only independent thing is A alpha, and all the other superfields can be expressed in terms of A alpha. That's absolutely right. Yeah. Or conversely, you see all the independent information already in the theta expansion of A alpha. You start with a gluon in the linearized order in theta. Then it goes on with a gluino, and there's an alternating pattern. Third line does once again refer to the gluon. Here I'm using the definition of the linearized field strength written down here. So this linearized field strength is just the curl, momentum with a polarization vector antisymmetrized, and this is gauge invariant at the linearized level. Okay, so whenever you see an F, it means that there is k times epsilon. So from this term to that term, you go 2 orders higher in theta, and 2 orders in theta count like a momentum. Yeah, you see I'm pretty lazy about how many orders I'm displaying. Since theta is a 16-component spinor, This is a series that goes all the way up to 16 powers of theta. For sure, we won't need them. I will later on give you arguments that the only thing you need for tree-level calculations is up here, up to and including the third order in theta. But for loop calculations, you need to go higher. Yeah. So also don't worry about all the orders of theta that are suppressed here. There are closed formula around to get as high as you wish in this theta expansion. And yeah, just to say it once more, it's always the same kind of component fields which you see at various orders in theta.
But epsilon and key are constant or at most dependent on the momentum.
Okay, they are implicitly depending on the momenta in the sense that they satisfy.
Okay, but they do not depend on x or anything because we have.
Oh yeah, right.
Fourier transform there already.
Absolutely, absolutely. Yeah, that's important to stress. Thank you. So all the x dependence and theta dependence on the right-hand side is completely explicit here. Absolutely. Yeah. Okay. Yeah, if you want to look up the closed formula for higher orders in theta, I can give you a reference for the closed formula. This is Munich production, Dimitrios Tsimpis and Giuseppe Policastro. Okay. In that Harnad-Schneider gauge, absolutely. Okay, so this is 10-dimensional super Young-Mills along with its equations of motion and a possible way to solve them. Now I will switch back to the worldsheet description of the pure spinor superstring and try to convince you that you find this field theory in the massless vertex operators. Any question on 10-dimensional super Young-Mills before I do so? Okay, so we'll do the massless vertex operators now. The driving force is the BRST charge, which was introduced yesterday as this contour integral of lambda alpha with d alpha. And we want to check out what is the cohomology of that BRST operator at the level of massless states. And a first observation, which will simplify that task tremendously, is to notice it doesn't mix different orders in lambda. It's homogeneously linear in lambda. So there's a clear grading with respect to the ghost number, the numbers of lambda. So we can do the cohomology analysis order by order. We can study the cohomology separately at each ghost number. So let's start off with ghost number 1. So here, when it's about ghost number 1, let me make an analogy with the RNS formalism. The analogous RNS vertex operator with ghost number 1 is C times the RNS vertex operator. The idea is that lambda is in some sense analogous to the C ghost from RNS, namely that the places where you insert a lambda, these are the punctures that you fix to freeze the Möbius transformation redundancy. And taking this analogy for granted, let's notice that the RNS vertex operator has conformal weight 0. So at ghost number 1, we want to have the pure spinor incarnation of a fixed vertex operator. That's a vertex operator that we don't the surface. So this must be of conformal weight 0. Without integration, the only way to be conformally invariant is to have conformal weight 0. Okay, so what can I do at conformal weight 0 and ghost number 1? Let's make an ansatz. What is the most general expression that is compatible with these boundary conditions? Oh yeah, I just wanted to indicate, yeah, that's the super ghost charge. I just wanted to indicate that this is agnostic to the super ghost charge. Yeah, thank you. Okay, so what is the most general thing we can do with ghost number 1, conformal weight 0? It must be something linear in lambda. So you need some Wild spinor to contract that single lambda. And let's for the moment take this object A alpha to be a completely unconstrained, a priori unknown object. It's just something that contracts the lambda. And we want to stay at conformal weight 0. So there's a very restricted choice of worldsheet fields that we can stick into this A alpha. It cannot depend on D alpha, for instance, because D alpha has conformal weight 1. So the only conformal weight 0 ingredients are X and theta. But the appearance of X and theta is not constrained by conformal weight 0. So I can put an arbitrary spinorial function of X and theta in here. I mean, a spinor valued function of the conformal weight 0 fields. Okay, and for the X dependence, like in RNS, we make an ansatz in terms of plane waves. I mean, it's just Fourier transformation as usual. And here you see it once more. I took the liberty to rotate the momenta by a factor of I. My apologies for that. But I'll try to be self-consistent with that in this lecture. Right, that's true, absolutely. Thanks. Okay, so let's now take this ansatz and impose that we are BRST closed. So now this will help us to learn more about the A alpha. So how does what does QV equals 0 imply? So here we need the OPE of D alpha with an arbitrary superfield S. Yeah, this capital S up there can be anything like A alpha or some later superfields. This OPE of D alpha will spit out a fermionic covariant derivative. Okay, so this is the condition for BRST closedness. Well, at first glance, this might not look that familiar, but let's now recall that lambda obeys the pure spinor constraint. So if we recall this fundamental constraint, then the BRST invariance condition is equivalent to the following. Okay, so let's notice that lambda alpha, lambda beta is symmetric in alpha beta. So we only get a constraint on the symmetric part of D alpha A beta. Let's now do some representation theory. If you have a symmetric bispinor in 10 dimensions, a bispinor with the same chiralities, there could be a 1 form and there could be a 5 form. And if we want this to vanish, and we have two lambdas sitting out there, it means that this symmetric part must be a pure one form. And this one form can a priori contract with anything. Putting it differently, take this statement here and insert it up there. Then lambda alpha, lambda beta will contract into the one form. And this gives you 0 by the pure Spinor constraint. This is a roundabout way of saying the condition for BRST closure lands us on the linearized super Young-Mills equation. You can conclude there must be some AM out there such that you can express this bispinor like that. So at this point, that vector AM is arbitrary. Oops. Or unknown. Okay? So in other words, we have just reproduced one of the linearized equations of 10-dimensional super Young-Mills. And let's now go a little step further. We want to have the cohomology of the BRST operator. That means V should better be closed, but also V should be non-exact. Or conversely, there is a freedom to shift V by Q exact quantities. So a shift of the following form is BST exact. So this is our gauge redundancy. And by matching this with the ansatz, lambda alpha A alpha, it means that we get a freedom in A alpha to shift it by some D alpha omega. But this is nothing but the linearized gauge freedom of 10-dimensional super Young-Mills. So these 2 points, BRST closure and BRST non-exactness, this reproduces parts of the 10-dimensional super Young-Mills data. It reproduces one of the equations of motion and part of the gauge freedom of 10-dimensional super Young-Mills. Yeah, so this is what we can pull out from ghost number 1. Yes, please. Right. Okay, so in a most generic ansatz for a bispinor, there could be something like this, contracted into a 5 form. But this 5 form must actually vanish, yeah? Because here, the contraction with 2 lambdas should give you 0. So take the right-hand side and contract it with 2 lambdas. Here, putting 2 lambdas left and right, this is completely non-zero. This won't work. You must insist that the symmetric bispinor is a pure 1 form. You can't afford having a 5 form in here. Yeah. Or you can also turn this upside down and require the left-hand side to vanish when contracted against the 5 form.
If you perform a filter arrangement or lambda alpha, you get only few terms. Performing the decomposition of the filter arrangement.
Right.
You expand lambda alpha, lambda beta, you get only a few constraints.
Yeah, right. It's only the 5 form for the fields. Yeah, absolutely. That's one way of phrasing the implications of the pure Spinor constraint. Right. Okay, so this was the story about ghost number 1. Let's now move on to ghost number 0. So this will be the analog of the integrated vertex operator in RNS. And here we are looking for a field of conformal weight 1, because it should be conformally invariant upon integration. Yes?
Because doing like this, it seems we are only going to find the massless states, right? But
Oh yeah, the headline is Massless vertex operators. I'm sorry that I didn't spell that out clearly enough. K-square was meant to be 0 from the first line on. Of course, you can do the same kind of analysis for massive vertex operators, and there have been recent results on the integrated vertex operator, the first mass level. Right, I mean, the procedure I'm explaining here, it easily carries over. It's just more zoology of different combinations. As you were saying before, the exponential has a conformal weight proportional to k-square. If you want to have mass level 1, then you need to put everything into your ansatz of ghost number 1 and non-zero conformal weight, say 1 unit of conformal weight. Yeah, absolutely. Okay, so here we are looking for the integrated vertex operator. At h equal 1. So it's the same situation as before. Oh, yeah. We specify the ghost number, we specify the conformal weight, and now we make an ansatz. We write down everything that is compatible with these constraints. And here it's obviously more to write down. So let's take everything from the set of conformal fields that has conformal weight 1. And again, at this point, please ignore the fact that you have seen these symbols before. Let's pretend we don't know yet what 10-dimensional super Young-Mills is. You just need some superfield with the right index structure. Something to contract the left-handed Weil spinner, something else to contract the right-handed Weil spinner, something to contract the vector, something to contract the two-form. We just need some functions of, okay, same as before, we can still play with conformal weight 0 data. So these guys can still depend on x and theta without altering conformal weight 1. Yeah. So this is the two form that the two form built from the W and lambda variable. Right, and here the x and thetas are sitting in the accompanying superfield. Yeah. Oh yeah, sorry, this I should have pointed out. Yeah, there is a balancing between the negative ghost charge. Yeah, right. That deserves to be spelled out. Good, we have found our ansatz. Now we again play with the BRST charge and impose closure as well as non-exactness. And okay, as you can imagine, there are plenty of OPEs to do now. Let me fast forward to the result. If you want to get this BRST invariant, then the superfields in there should better obey the equations of motion of 10-dimensional super Young-Mills. Oops. So I was always phrasing the linearized equations of motion as a statement on the d alphas. And you will probe all the d alphas here by acting with the BRST charge, because there is a d alpha in here. On the superfields, d alpha acts like the covariant fermionic derivative. Sorry about the many d's. Little d alpha becomes capital D alpha. So by imposing BRST closure on that, you can basically solve for the d alpha of anything here. Yeah, you can learn what these expressions must be, Carlo.
But here you are at those numbers. These are the integrated vertex.
This is the integrated. Okay, that's the next thing I'll get to. You are right. There is.
You want them, when you do the BRST, you get the
Okay, that's true. And this derivative, I'll write it down shortly, is of a very specific form. There are still meaningful statements. You immediately zero anything which cannot be a total derivative.
Okay, so
Yeah.
something must be zero because it cannot be a total derivative.
Exactly. You zero everything which is not a total derivative. Yes, that's the fine print that comes in the next line. So if these guys obey the linearized equations of motion, then you get, yeah, it's indeed this line here in my manuscript. What you then find as a reward for satisfying the equations of motion, you get the following structure here. So I'm now spelling it out in detail what you get. You get this stuff, and as Carlo was saying, this is a total Z derivative. Why is that the case? Let's go in Leibniz through that. The dz can act either on the lambda alpha or on the A alpha. Here's the obvious contribution. And now, if you hit the A alpha with the total derivative, we apply the chain rule. A depends on Z through X and theta. And this is tracking the dependence on X. This is tracking the dependence on theta. And there are some mutually compensating shifts between pi and del X, and this one and the pure theta derivative. So what matters is that this stuff here is Z derivative of A alpha, evaluated with the chain rule. Okay, and why are we satisfied with that? Of course, the best case scenario would be to get 0 on the nose, but U will always be integrated. So it's absolutely fine if we arrive at a total derivative here for the BRST variation. I told you yesterday, total derivatives in presence of the Kober-Nielsen factor integrate to 0 when they are taken with respect to the punctures. Yeah, so this is fair enough. With this kind of BRST variation, we have managed to generate a BRST invariant integrated vertex operator. Okay, so let's move to the... Oh?
I was thinking about if you could play the same game with ghost number 1, but there is no meaning of asking a total derivative because it is not integrated.
Yeah, exactly. Also, can you propose a total derivative of conformal weight 0? Maybe a tachyonic one. Yeah. Okay. Yeah, so this was the story about BRST closedness. And also we should check the issue with BRST exact states. So let's again note gauge freedom in the integrated vertex operator. Suppose you do a simultaneous transformation of A alpha and AM. Suppose you add this one to your integrated vertex operator, then what you will get is again a total Z derivative in disguise, namely it's the same calculation that we had a few lines ago, that what you get from this what you get from this gauge freedom is once more a total Z derivative. Okay, so let me wrap up. We have... Yes?
How can you identify that A alpha with the previous A alpha?
Ah, yeah, that's a really good point. it's this equation which builds a bridge between the QU and V. And you're absolutely right. What if I use, say, a B alpha, which is independent from the A alpha up there? Yeah. There's one stage in the tree amplitude prescription where you need to insist on that. Namely, I will later on claim that the tree amplitudes are independent on which states you put in the V vertex and which states you put in the U vertex. And the tree amplitudes are only independent on this choice if it's the same, A alpha, in both vertex operators. Uh-huh.
But different from RNS, here you are able to express a vertex for a field strength, which is a little...
I don't think this is in any way a problem. Just compare with the RNS term, double psi. If you look up in your notes, you will find that this is the coefficient of psi psi. So also there you find a field strength. So if you, yeah?
In which picture?
That's the zero picture in RNS.
This is a term on the vertex, which is Dex, which is not the field strength, but is usually associated with gauge field. But in picture it's zero. This term is associated with the gauge field X, not the reverse field strength.
I mean, there's a mixture of both. I mean, here you have the potential, here you have the field strength. So it's a democratic expression. You have both of them in here. And this is precisely what we have in RNS, because in RNS there were the two terms, epsilon del X plus psi psi field strength. So it's really the same kind of mixing in the RNS formalism, that both the potential and the field strength enter the vertex operator.
So let us say it that way. If you take U and you put, can you simply compute the amplitude with only F?
You mean discarding that part?
Yes.
Well, I don't think that the BRST invariance would go through. I mean, in order to get this thing BRST invariant, all the equations of motion of super Young-Mills must hold. And if you look them up, these equations of motion, they strongly entangle A alpha, AM, W, and F. I don't think you will arrive at a... Yeah, it's really BRST invariance that fixes the story. And you saw it in the 4-point calculation we did here, how important it is to have both of them in the vertex operator. I mean, just confirming once more that you should better work with BRST invariant vertex operators. Okay. Yeah, so let me wrap up. We have now found two massless vertex operators, and now we will see how we can mash them together to build tree amplitudes. I'm sorry? Oh, give me 2 minutes, you will see it. Okay, let me start by writing down an expression and then discuss its properties and try to argue why it's a good expression. So as before, we are just looking at a color-stripped tree amplitude. So I already commit to a disk ordering, to an ordering how the open insertions are placed on the disk boundary. I'm again parameterizing the disk boundary by the real line, and I'm in the usual SL2 frame where Z1, Zn-1, and Zn are 1 and infinity. Okay, so that's the integration we'll do. And now, given the 3 fixed points, as usual for genus 0, we need to use the unintegrated vertex operator 3 times. And we need to make sure that this harmonizes with our choice of fixing. For every integration variable, we should use the U vertex operator. Putting it differently, QU gives a total derivative. You should really integrate the U's, otherwise you have a problem with BRST invariance. Okay, so these are the n-3 integrated vertex operators associated with the integration variables. And then there are 3 instances of a position-fixed vertex operator V. Okay, and I was already telling you before, amusingly, this expression for the endpoint amplitude is independent on how you distribute the V's and U's. Of course, you must use a total of 3 position-fixed vertex operators, but it doesn't depend on which of the 3 legs you choose that are represented like that. This is not particularly obvious at first glance, but in order to check that, you must essentially make use of this relation connecting U and V. It's maybe half of a page of a calculation. I won't do it here, but I can give you a reference to a Berkowitz paper from 2000, where he shows this explicitly. So let me just remark that the proof is essentially an application of QU equal del Z of V. Okay, so after talking about this first sanity check, let me comment on how you can evaluate or simplify that. Yes, please.
So even if it is an integrated vertex operator, do you have a constructive way of building U?
Oh, yeah. Right, yeah. Okay, okay, the B ghost is explicitly known in the non-minimal pure Spinor formalism, but the expression for the B ghost is not particularly inviting to evaluate B action on that. And I think a state of the art example is that paper on the integrated vertex operator at mass level 1. I think there the authors again proceeded from an ansatz. I would assume that they thought about using a constructive procedure. But I'm not aware of any constructive procedure which is more efficient than an ansatz. You mean there's some BRST trivial admixture? Okay, well, I wouldn't say this is a problem. This may be an inconvenience, but yeah.
That's the answer for this question, because you can add with B on U in order to get B, right?
Sorry, you mean B on V to get U?
No, B on the integrated in order to get the integrated.
Sorry, you start from knowing.
Yes. Sorry, is B acting on the integrated? Right.
Yeah. Yeah. Okay. Okay. As a next step, I want to sketch a strategy to evaluate these correlation functions to get something more explicit for the tree amplitudes. So it's a 2-step procedure to evaluate the correlator. And it's just the skeleton of a strategy. I will spend a lot of time to make refined explanations on how you do these 2 steps in detail. But to first of all give the structure of the task ahead of us, we want to do a path integral. We want to integrate out all the modes of the conformal fields on the worldsheet. And let's start with the non-zero modes. Integrate out the conformal weight 1 fields, namely all of those which you see in the integrated vertex operators. Integrate out the h equal 1 fields, and this amounts to using the OPEs from before. Okay, and when you integrate out the h equal 1 field, if you sum over all the singularities they can produce, you automatically check out the non-zero modes of the conformal weight 0 fields. There's an OPE d alpha hitting the thetas. Even though theta has conformal weight 0, its OPE with the alpha will take care of the non-zero modes. So this step of integrating out the h equal 1 fields will remove the non-zero modes from the path integral.
The reason is that you want to have the zero modes of theta and x as a really superspace.
Oh yeah, precisely. The zero modes of theta are going to be the variables for pure Spinor superspace, both lambda and theta. Yeah.
Otherwise, you would do this in 2 steps. You would at least at the level of NSR, you would perform everything in 1 step using your OPE.
Yeah. I agree. There is no established RNS analog of this strategy. And I want to stress, it's not a must statement. I wouldn't force anyone to do it like that. I'm just describing this as a convenient procedure to attack the task. Yeah, maybe there is a way to do something analogous in RNS. And I don't really know of any RNS analog. Yeah, so once we have taken care of the non-zero modes, the leftover homework is to integrate over the zero modes of the conformal weight 1 fields, conformal weight 0 fields. We are at genus 0, so therefore, in order for a conformal field to possess a 0 mode, it must have conformal dimension 0. So the candidates we have in the pool are these guys. They both have conformal weight 0. You might also think of the field X, but there the 0 mode gives the momentum conserving delta function, as we have seen in RNS. So there's nothing new to say about that. The 0 mode of X is just giving momentum conservation, so I won't discuss it. At genus 1, this is definitely the case, but here we are doing tree level. Yeah.
E to kx is considered 0 in the first or the second point?
Okay, e to the ikx or kx. Yeah, right. So there's the big X, which decomposes into a 0 mode, plus all the oscillators. And the oscillators are probed by the OPE. By the OPE against the... Yeah. So when you integrate out the pi field, you will probe the oscillators. So to answer to your question, this is done in step 1 here, the oscillators. And okay, the 0 mode, strictly speaking, this is step 2. But since I'm confessing that I won't track the delta function, it is, not really entering the, yeah, it is. Yeah, so there are 2 leftover fields that we need to worry about. We will need a 0 mode prescription for theta and lambda. And let me write down the answer and then try to convince you that it's a good choice. What will probably find everybody's approval, we need to worry about trilinears in lambda. I mean, looking at this correlator, we have 3 insertions of the V vertex at ghost number 3, and there is no surviving lambda in the U vertex. So we need to worry about trilinear in lambda. But how many thetas? So this is probably the less intuitive piece. And the answer turns out to be you should take 5 thetas. And you should furthermore look at this strange-looking tensor structure, which begs for a lot of justification. Okay, so this contraction of the type lambda 3, theta 5, is set to a constant. Okay, there is a freedom of normalizing. Other people would write a 1 here, but for some purposes, the 2880 might be more convenient. But, okay, why the hell is it lambda cube theta 5, and why the hell is this particular tensor structure? Okay, so let me start by talking about the tensor structure. I don't even need to spell out the tensor structure because it is unique. Here it is representation theory in action. We are looking at pure spinors. And if you have a multilinear in pure spinors, this is going to sit in a very particular representation of the Lorentz group. So if you're a fan of Dynkin labels, I can make the statement quite precise as that. If you take a n-fold tensor product of pure spinors, what you do is you just raise the corresponding Dynkin label to the nth power. Or, yeah, you're taking this, you're landing in this particular representation. And anything else is killed by the pure spinor constraint. So now you know where lambda cube lives. About the thetas, here you have a 5-fold antisymmetric tensor product. And now you can check how many scalars can you form by tensoring the 5 thetas into the lambda cube representation. You can use the Lie online service, for instance, to evaluate that tensor product, and you find a single scalar. So in other words, there can only be one tensor structure. If you happen to find another one, which gives non-zero, it will be proportional to this one by representation theory. So strictly speaking, I don't even need to spell out the tensor structure. Okay, so in summary, it is the pure spinor constraint which helps us once more, though here in a more roundabout manner. Good. So what else can we say about this? If you look at the content of the angular bracket, this lambda 3 theta 5, it is Q closed and non-exact. Okay, Q closure is easy to check. You have the expression for the BRST operator. You know the OPE of d alpha with theta. It's easy to check that this is a BRST closed. But what about non-exactness? Well, how can we prove non-exactness? If there was a BRST ancestor for that, then it would be of the form lambda square theta 6. I mean, hitting this with D gives you lambda cube theta 5. So if there is a BRST ancestor, it will be of that form. But now we can again run representation theory. Is there a Lorentz scalar with this structure? And the answer is no. By representation theory, you can't construct such an object. Again, use the Lie online service. Okay, so these are 2 good reasons to like this choice of zero-mode prescription. Now, you could ask, what about a different power in theta? What about lambda 3 theta 9? Well, 2 reasons why this is not a good choice. You will shortly see the 3-point function, and you screw up the mass dimension if you pick out a different power of theta. And as a more abstract and rigorous argument, as far as I know, the BRST cohomology is empty if you try it with theta cube and a different power of theta. So if you just scan all the choices, theta to the 0 all the way to theta to the 16th, compatibility with the cohomology forces you to take 5 thetas.
I mean, that thing should be the only cohomology representative across number 3. That's equal to the bracket.
Right, made of, yeah. Right, exactly. Something like the anti-field. Right. Okay, so these were some more general comments about the zero-mode integration. Let me also share some tools and tricks in practical calculations. Due to this cohomology problem, you can do BRST integration by parts. What this means is you exploit that BRST exact quantities give you 0 under this bracket. So this allows you to do certain manipulations. Suppose you have something Q exact in your bracket, but also some spectator, which depends on lambda and theta. Then you can do an integration by parts to have Q act on the other factor here. And whether you get a plus or minus, it depends on the statistics, whether X is a boson or a fermion. So this is a move that is really, really helpful in simplifying pure spinor amplitudes, or in general to simplify expressions in pure spinor superspace. Oh yeah, I haven't introduced that term. If you meditate about functions of lambda and theta, which you later on insert into this bracket, this you can view as the definition of so-called pure spinor superspace. And this is where the string amplitudes in the pure spinor formalism will more really live in. Okay, so you can do BRST integration by parts with this bracket prescription. And maybe one last and particular important property. Suppose you have identified a superfield which is BRST invariant. And suppose you have obtained such a superfield from the 10-dimensional super Young-Mills theory. I mean, all the examples in the subsequent will be about A alpha, AM, W alpha. We will feed all of this with 10-dimensional super Young-Mills superfields. Yeah. Suppose you have a BRST invariant combination of 10-dimensional super Young-Mills fields, and you stick it into the bracket. Then you get something really pleasant. You will get something gauge invariant, and supersymmetric. Yeah? So just imagine you're applying the lambda 3 theta 5 prescription to something like here. Then you get functions of polarization vectors and also gaugino wave functions. And you have the promise that all of this will be gauge invariant and supersymmetric if it descends from a BRST closed superfield. So it is extremely valuable to know about BRST invariant combinations of 10-dimensional super Young-Mills stuff. Mm-hmm.
So this is a homology representative of number 3, so it can only be one.
Okay, at 3 points, it is the 3-point function will be the unique answer. However, starting from 4 points, you can construct more such BRST invariants. Or in particular, tree-level endpoints will lend you an n-3 factorial such solutions that are compatible with the mass dimensions of a tree amplitude.
Yeah, but they should all end posators or abstract, because it is just the homology is one dimension, so that's possible.
Well, they will be relabelings of each other, but I don't think that they will be proportional to each other. I don't think that.
Shouldn't they be just all those? Because any endpoint amplitude will boil down to this expression that you said equal to 2080.
Right. Okay, so this is how you evaluate the components of the tree amplitudes. But in simplifying the correlator, I think we get n minus 3 factorial different superfields, which are not BRST equivalent to each other. And they will evaluate to a BCJ basis of super Young-Mills amplitudes in components. Or maybe you can ask me again once I spell out 4 and 5 point functions, and it's probably easier to see where, yeah. Yeah. This is about the zero mode. So I'm pretending that we are in a stage of the calculation where everything of conformal weight 1 is gone.
So it means that the non-zero modes of theta has been traded with the d alpha, exactly as with the...
Of course, you can also think of what happens if there's a d theta and no d alpha. Then you simply get 0. Yeah.
So it means, in a way, you are saying that there are 5 zero modes of theta in order to get a non-vanishing expression, means that you must have 5 zero.
Yeah, roughly speaking, the pure spinor allows you to integrate over 5 thetas in a Lorentz covariant way. That's
Also another way of saying,
yeah.
because you have 5 components.
So also way before superstrings, pure spinors have been noticed as a nice gadget to describe 10-dimensional super Young-Mills. Like the equations of motion can be phrased as QV equals 0 and so on. Yeah. Okay. Any further questions on the generalities of the tree amplitudes? Yes. 0. Yeah. Sorry, what happens? Yeah. Each spinor component has 1. Yes. Maybe a more useful way to think about this is a definition of the bracket, a definition of your path integral, about this part of the path integral that is sensitive to zero modes. I'm sorry? Okay, more rigorous. Yeah. Okay, I mean, I was giving indirect arguments. I don't know on top of my head a direct path to arrive there. But I would... Yeah. Any other choice is not compatible with the cohomology structure. Not the most satisfactory answer, I admit. Okay, this rather abstract prescription calls for a 3-point example. And we will now pull out the Young-Mills cubic vertex and also the gluon-gluino coupling from this prescription. And we will use the most convenient gauge, namely this Hanard-Schneider gauge that I mentioned before, where we have a very useful organizing principle for the theta expansion. So the schematic structure of the theta expansion over there is that, first good news, A alpha starts at the first order in theta. There is no theta to the 0th term. Yes, please? Oh yeah, I think in 5 minutes is an excellent time to do this break. I agree that we should do this. Yeah, so let me remind you of this schematic structure of the theta expansion of A alpha. So this is the thing that we will have in the V vertex operator. So let's insert this theta expansion into the 3 vertex operators, each of which is a contraction of this form. Good. The task is to isolate the theta cube lambda 5 part. Okay, theta cube we have manifestly everywhere. We only need to worry about having 5 thetas. So how can we get 5 thetas if we have 3 superfields of this type? So we need to think about partitions of 5. And there are 2 inequivalent choices how to do this. You can partition the 5 as 1 plus 1 plus 3, or as 1 plus 2 plus 2. There is no option to take a 0, because we have gauged away the 0th order in theta. So the only inequivalent partitions are of this type, and I'm writing 3 times 2, because you can of course take cyclic combinations. Okay, and everything else is basically here on this blackboard. We will now have 2 inequivalent calculations to do. The line here refers to the 1 plus 1 plus 3 partition. So here we are looking at a contribution where each superfield contributes a boson. Remember, this F is nothing but k dot epsilon. And the other partition that was loosely referred to as 1 plus 2 plus 2, this amounts to picking up 2 fermions from the respective theta expansions. Okay, and for each of these calculations you need to add the cyclic friends where you relabel the polarizations and momenta. Good, so after reshuffling things a little bit, you arrive at these theta cube theta 5 expressions. But if you take a careful look at the indices, they are not in the same form as there. So this is the point where you should ask your money back. I was only giving you the completely contracted version of the indices, but this is not on the nose the same as that. But the resolution is again a matter of representation theory. There's again just a single Lorentz scalar in that tensor product there, and if they are unsaturated indices, then you need to write down the Clebsch-Gordan coefficients with the same index structure. So here, this is something antisymmetric in RNS. This is something which will be proportional to this one. There's nothing else that you can write down with 4 vector indices and the antisymmetry in RNS. So it must be proportional to this, and the coefficient, this you can determine by contracting that equation with more or less the inverse of that. So at some point you will be able to map it to the already normalized quantity. And if you do this carefully, you will find 32 as the answer. That's completely determined by representation theory, and likewise here in the lower line. If you look carefully, you have 1 free vector index and 2 free Spinor indices, and there's just a single Clebsch-Gordan coefficient that it can be. And to find the prefactor, you again contract it. So here you find the answer is 18. All right, when the dust settles, by plugging everything together, you will find that this 3-point function is giving you something bosonic, and something fermionic, whoops. And if you carefully track the labels, then the first one should be something like this one and that one. Okay, happy end. What we have is nothing but the Young-Mills 3 vertices of the theory. So the first thing is nothing but the 3-gluon vertex of super Young-Mills, and the other one is a vertex with 2 gluinos and 1 gluon. maybe an unusual way to derive these cubic couplings, but it's just to show you how this prescription works in practice and how you can start in pure Spinor superspace and arrive at these component expressions. Okay, so this is really the moment for a break. Hey, is everybody back? Okay, yeah, thanks a lot for the interactive lecture we just had. I'm glad that you were carefully following and then spotting the open questions that I was leaving in the first attempt. So now, in terms of the timing, I'm a little bit in trouble that on the one hand, there's a lot to say about the endpoint function here, but on the other hand, there are further topics waiting, including double copy, zeta values, and so on. So may I suggest the following experiment, that I give you a compressed version of deriving the endpoint function, which will probably keep us busy for the rest of today, such that tomorrow we can start with new topics, like closed strings and all that. Yeah, so this means the lecture now will be more sketchy, and in case you don't understand everything, let me assure you, you can already get the nuggets from the first 3 lines. What this lecture will be about is the endpoint function. This is the result of a calculation done in 2011 together with Carlos Mafra and Stefan Stieberger. And the idea is to work with the formula up there, to follow step 1 and step 2, integrate out the non-zero modes, later on integrate the zero modes, and to arrive at a neat formula. So, as you see, the main challenge is a good handling of the OPEs. So, what I try to sketch in this lecture is an organizing principle for the OPEs. This gives rise to a notion of multiparticle superfields. This means to talk about the residues in the OPE, what you get on top of the simple pole in the punctures if you do OPEs. And even though I said that the calculation was firstly done in 2011, we noticed in the years thereafter that there were some shortcuts that we missed. So if you want to read about multiparticle superfields, for sure the ancestors go back to 2010 and 2011, but a lot of the cleanup work has been done in this paper, and even further cleanup in terms of the component extraction appears in a later paper. Right here. Okay, and by means of these organizing principles for OPE, one can arrive at a structurally interesting result for the endpoint function, which I'm summarizing as follows. You saw it in the introductory example on Monday. If we play with the 4-point function of the open superstring, you can factor out a 4-point function from the Young-Mills gauge theory. And at 4 points, the expressions are still comparably slim, but what was not at all obvious at that time, something similar can be done for the endpoint function, that you can put all the polarization dependence into the corresponding gauge theory trees. And one reason that this hasn't been noticed before was
it's not one-to-one. If you're interested in a specific color ordering on the string theory side, what we will always arrange by adjusting the integration domain, then on the right-hand side, you get a variety of different color-ordered amplitudes in super Young-Mills field theory. So to explain the notation, I'm summing over permutations of n-3 legs, namely all the legs 2, 3, ... n-2, which are enclosed in this parenthesis along with rho. And it's not a coincidence, these n-3 legs here that will be permuted are the same ones that are represented by the U vertex in here. Okay, so super Young-Mills trees are part of the result, and then there must be some alpha prime. So for each color ordering row, there is a different function depending on alpha prime, and here I'm back to the dimensionless Mandelstam invariants. And these are obviously descending from integrals of this type. With the usual n-point Kober-Nielsen factor. And most importantly, the denominator is keeping track of the OPEs. Each time you do an OPE, you introduce a factor of zi minus zj in the denominator. And yeah, it is precisely known for the endpoint function which kind of differences of z's are down here. So just to repeat the notation, Zij refers to a difference, and for the Kober-Nielsen factor, I'll just use the shorthand notation In. Okay, so suppose we are inside a math textbook. This is the claim, and the rest of the lecture is the proof, or at least a sketch of the proof.
Is that a kind of refinement or improvement with respect to the usual formula? You would sum over the cyclic permutation of n-1. This is just the permutation of n-3.
Do you, yeah.
The first one
Okay.
and then
Oh, I'm not sure whether I agree. You sound like you have in mind the formula to get the color-dressed tree amplitude. What you do is you sum over all cyclically inequivalent traces. Okay, and indeed you need permutations of n-1 legs here. Okay, and what happens here is something else. We are taking the magnifying glass and look at an individual color-ordered amplitude. Yeah.
so you are just taking a one color order and
Yes.
splitting again up into sub-pieces.
I'll try tomorrow to illustrate the bigger picture of how these combinatorial games with n-1 factorial and n-3 factorial, how they are intertwined, both in gauge theory, gravity, and open and closed string theory. There's a lot of parallel in structures, whether you look at field theory amplitudes, string theory amplitudes, and even the open string is a little bit like a gravity amplitude in a way that I'll explain tomorrow. Yeah. Okay, so the goal is to, at some point, decompose that formula into tree-level amplitudes of super Young-Mills. So for sure, one of the tasks is to recognize when you have produced a tree amplitude of super Young-Mills. So roughly speaking, the idea is to have a superspace representation of Young-Mills trees. The first one you see up there. We started with the 3-point open string amplitude, which is V1, V2, V3. And we noticed that at the end of the calculation, there were no alpha primes. So we noticed that this is nothing but the super Young-Mills 3-point function that we computed. So the pure Spinor superspace expression for the 3-point function is V1, V2, V3. So in order to recognize the n-point function inside that stringy calculation, we need to know what's the pure Spinor superspace stuff that reduces to the n-point function of super Young-Mills on the right-hand side. That's the thing we will need. And in order to give some intuition how this comes about, let me try to walk you through the 4-point example. Okay, so by taking the above formula, we will attack the 4-point function from this opening line. And this is a good opportunity to illustrate the two-step procedure. You didn't really see the step 1 happening because there were no conformal weight 1 fields in the 3-point example. So we need to integrate out the h=1 fields here. So putting it differently, we need to determine this 4-point correlator using the OPE between V and U. Okay, there's a single U, and this one will have OPEs with the different V's at position 1, 3, or 4. And as a little benefit of our SL2 frame, we don't need to worry about the 4th vertex, because if you look at its OPE with U2, you'll get a denominator of this form, but we are sending Z4 to infinity. So let's not worry about that one. So there are only those terms where you OPE U2 against either V1 or V3. Okay, so what do you get here? For sure, there are plenty of chances to generate a simple pole. Just to give a few examples, there's a pi m field at the position Z2, and there is an exponential at position Z1. This is a way to generate a simple pole. Another example, there is a pure spinor in the V1, and there is a Lorentz current of the ghost at Z2. Also this gives a simple pole. And finally, there is a d alpha that can act as a covariant derivative of the a alpha in here. Yeah, so many opportunities to pick up a simple pole. And let me now organize the outcome in a particular way. I'll split the answer into a BRST exact part and some BRST non-trivial part. Okay, so this only makes sense if I tell you what A alpha is. So here I'm using 2 superscripts to label this A alpha, simply because it takes superfields at both positions, from 2 different external legs. Okay. I admit it might not be obvious at this stage how I choose my partitioning. You will see that shortly. But let me just say, for the rest of the calculation, we don't need to worry about the Q exact part. I told you that you can do BRST integration by parts. You can do BRST integration by parts, namely, when you track this in your 4-point function, this Q exact stuff will be multiplied by V3, V4. And using that BRST integration by parts, you only need to act with Q on V3, V4. But since V3 and V4 are both BRST closed, this doesn't contribute. So in other words, you have the opportunity to get rid of all the BRST garbage that you don't want to carry around through your calculation. Yeah? So you only need to worry about this stuff here. Yes?
A12, okay, is always ground is a multiple field, square field.
Yeah.
So it is, you started with two objects defined in two different points, worldsheet point.
Yeah.
But then you get a multiple field that are all in the same worldsheet point.
Oh, I don't think you need that. I mean, first of all, whether you put Z1 or Z2, this only differs by contact terms.
Yes.
So you don't even need to specify.
I was asking this.
Mm-hmm.
And the second is that, so the question was that A2 and what it was meant that all the polarizations are the polarization 2.
Yeah,
So you have
yeah,
polarization
right.
1 and polarization 2. So
But, yeah.
the point is, when you take this multiple field, you think it of one point of a worldsheet or a multiple point, let us say. Because obviously you use the lobe, you would consider that as one point of a worldsheet.
Yeah, okay. Strictly speaking, it is at one point, because when you follow this algorithm of integrating out one vertex operator after the next one, you want to give up the worldsheet position of the vertex you integrate out. So the exact answer to your question is yes, it's all happening at the same space-time point. But I think the more important point is, and I wasn't very clear on that, so thanks a lot for asking about that, the polarizations that are in there. Here, the superscript 2 means this depends on the external leg 2, on all the polarization data of external leg 2 only. Whereas the subscript 1 means this is a function of the polarizations of the first external leg.
So while alpha begins at theta, so A2 alpha A1 begins with 2 thetas at least.
Oh, no, sorry. Here I'm using a dot product notation. This is a vector field. I mean, it contracts the momentum, which is a vector. This is the A vector. Yeah. Yeah. So if you ask about the theta expansion of this object, you even have theta to the 0th terms from here. If I have the time for that, I'll give you a gauge argument later on that you can make this disappear, but it does start at the 0th order in theta. Absolutely. All right. Yep, you can probably imagine there is a reason to choose this funny notation, to again write A alpha, even if this is about 2-particle data. There are a lot of formal similarities between the A alpha before and this new A alpha. And to dwell on these formal similarities even more, let me introduce a notion of a 2-particle vertex operator. Yeah? For the old school single particle vertex operator, it was lambda alpha times the single particle A alpha. Now, there is information from 2 different states sitting in that object. So that's why I put both 1 and 2 into the subscripts here. So as some sort of justification for this notation is, let me talk about the BRST variation. So the defining property of the single particle vertex operator was this one. Now, in handing you this 2-particle friend of the vertex operator, I should better have a statement about its BRST variation. Computing it, it's nothing I want to do on the blackboard, but let me assure, all you need to do is hit all of these superfields with the alpha and keep your nerves and observe a lot of cancellations. So what you get is something really beautiful. After hitting this 2-particle vertex operator with a Q, you just get back single-particle vertex operators. This is something we call BRST covariant. Suppose you view the V as being in your toolbox. Q of the new object gives you stuff that you have already visited at lower multiplicity. And without giving you the exact definition, if you later look at the 5-point function, where you need to do iterated OPEs, there will be a chance to define an object V123, something we call 3-particle vertex operator. And the expression for that V3 itself, it requires a bit of notation to write it compactly, but what I can do on the spot for you is give you the BRST variation of that new object. Namely, it's again BRST covariant in the sense that Q of the big and new thing gives you combinations of old things. 2-particle vertex operators and 1-particle. Okay, so this kind of structure, as I said, I'll refer to it as BRST covariance. But okay, let's not get sidetracked. What we are about to do is simplifying or evaluating the 4-point function. Yeah. I think it doesn't matter because here at this stage you don't do any further OPEs. But in a 5-point context, in a 5-point context, the answer is yes. Yeah. Then you put them at the same point, and
The Q of V12 is equal to the product of the BST of V12 is V1 times V2. But this is a normal ordered product. Because it's at the same point, so
yeah.
or do they are any singularity V1?
Yeah. Okay, I think what you have in mind is a calculation of the form this one, acting on a superfield at Z1 and a superfield at Z2. This is probably what you have in mind. No? No, I think...
Okay, we can talk after.
Yeah. Okay, so what I had in mind was just lambda alpha d alpha. I wasn't doing any worldsheet techniques anymore because Q always acts through this covariant derivative when you're applying it to superfields. I mean, this is a stage where the conformal weight 1 fields are assumed to be gone. You're only left with the zero modes of lambda and theta. That's why I wouldn't track the positions on the worldsheet anymore. Okay. Okay, what I wanted to do next, I introduced you to this object V12, and this is the BRST non-exact part of the OPE, and this is in turn the engine for the 4-point function. So let's insert that result for the OPE into our opening line. There's the usual Kober-Nielsen factor. Maybe I spell it out once more. And now, let's insert the OPE. When we contract U2 against the first vertex operator V1, then we build up a V12. And this is on top of a single pole. Okay, in our SO2 frame, Z1 is 0, so maybe I shouldn't track it. Good, and if you do this OPE among the first two vertex operators, you leave the other two untouched. Good. Now, as you see from the two arrows above, you also need to look at the OPE with V3. But there's nothing new here. This is just a permutation of the first term. It's just reshuffling the labels here. So we have already done the hard work by identifying the V12. Okay? So this is good news. The 4-point function is reducing down to only 2 terms. So only 2 different functions of z in the integrand. And let's not forget, this is computing a hell lot of amplitudes for you, for gluons, for gluinos. So it's already remarkable that it's that compact. And let's make it even more compact. Let's make sure there's only one independent integral appearing. Let's do a total derivative insertion. Suppose we compute the total derivative of just the Kober-Nielsen factor, then what you get is this combination here. So in other words, if you look at this combination, you can equate those two integrals up to a ratio of Mandelstam invariance. So you can morally replace the second term by 1 over Z2 on the expense of introducing a ratio of Mandelstam invariance. Yeah, under a Kober-Nielsen integral, this can be replaced by that. Okay, so we can put everything into the same integral. This is the quantity that we have looked at in detail in lecture number 1. It has been dubbed Z4 point in lecture number 1, or it's the thing that you can write down as a ratio of gamma functions. All this to say, it's the same old friend that we already saw confirmed in the RNS formalism. Okay, so if we pull out that guy, let's be careful what its coefficient is. Okay, this might look a little bit odd to you. Let me insert k1.k2 divided by k1.k2. This is for bookkeeping purposes. Because then I get this cyclically symmetric combination inside the pure Spinor bracket. Yeah, sorry, just very cheap algebra happening here. But the reward for this, for these kinds of moves is the following. What we have inside the angular bracket is a BRST invariant expression. So if we BRST vary that stuff, Q only needs to act on the 2-particle vertex operator because this is BRST closed. Yeah, so the only contribution is from Q on V12. But this BRST variation introduces a K.K. So you will cancel the pole when evaluating the BRST variation. And the same story holds for the second term as well. Here you need to take into account that the V and Q are both fermions. So you pick up a minus sign when Q jumps here. Yeah. So what matters is the BRST variations will cancel. You get a BRST invariant quantity here. So both of the sub-variations give you a product of these 4 vertex operators, and you get a 1 minus 1 by canceling the second against the first term. So all this to say, we have a BRST invariant expression in pure Spinor superspace. Now, do you recall? What did I tell you before? If you're sitting on a BRST invariant superfield, what do we learn about its components? They are gauge invariant and supersymmetric, was the claim. So here, we are sitting on an object which is gauge invariant and supersymmetric, and it furthermore has two kinds of poles. This pole, which means in field theory language that we have such a Feynman diagram with some cubic vertices. Over there, this pole structure means we have that Feynman diagram. So in field theory terminology, we have the S channel and the T channel. So this smells pretty much like a 4-point color-ordered tree amplitude of 10-dimensional super Young-Mills. So the claim is, this object is, on the nose, the 4-point function. Because it is gauge invariant, supersymmetric, and compatible with the propagator structure you expect. For instance, through a Feynman diagram calculation. Okay, if you're really picky, you might be missing the 4-point Feynman vertex. As you know, there's a 4-gluon interaction already in pure Young-Mills, but if you evaluate the components, you might also find contact terms k.k, which cancel the propagator. So the 4-point vertex can be somewhere in here. And we all know the 4-point vertex is nothing but the gauge invariant completion of the cubic interaction. And since I just explained that this expression is gauge invariant, you can be sure that the 4-point vertex is properly accounted for. Okay? So the upshot of that is, by BRST manipulations, this is identifiable as the 4-point Young-Mills tree. And if you want to have its components, just go through the Theta expansion and pick up the lambda cube theta 5. And indeed, by explicitly evaluating components, it is fully confirmed to be the 4-point Young-Mills tree. Whoops. Yeah, so this is the end of the 4-point calculation.
Essentially, the issue with the 4-point conductor is that it is different from 0 even when all the momenta are vanishing. In this case,
You're in a kinematic limit? Sorry, what did you say?
the 4-point is non-vanishing also when all the momenta are 0. Because there are no derivatives.
Okay, you mean there is a... Yeah.
Or when all the momenta are collinear, let's say, this way.
Okay, yeah.
If you want to do 0.
Okay, of course you need to be careful with the singular terms as the momenta go collinear, but yeah.
You cannot really go to that limit because everything explodes there. Because
Yeah.
pole 1, S1, 2, 1, S2, 3 would be 0, strictly speaking.
Yeah.
They are collinear. And
Right.
because the term arises from one of the Z, which is
So you mean the infrared divergence encoded here? Yeah, okay.
you get some issue
Right.
from that point.
Yeah. Okay, I didn't attempt to go into infrared divergences. I was already happy by seeing that it's the same result that you would get from a Feynman diagram calculation or more sophisticated on-shell methods. Yeah.
Anyway, this problem would be exactly the same in Superstring.
Absolutely, that's... Okay, so to summarize, the 4-point calculation is pretty compact if you have the V12 into your toolbox. So once you already have all the multiparticle superfields, you can check in front of your eyes that things are BRST invariant and can be aligned into a single worldsheet integral. So let me now approach the 5-point example with the bold assumption that we already have the V123. I can't demonstrate it now, but you have my word that all the OPEs, and there are 2 of them at 5 points, all the OPEs will at the worst give you a V123. It's probably simpler to write down the explicit expression to make you see this. Whoop. Or to give you a chance to see what I mean. Whoop. So at the 5-point level, we have a double integral, a 5-point Kober-Nielsen factor. Okay, and let's just do the combinatorics in our head. What kind of possibilities do we have to perform two OPEs in this expression? Okay. I try to be quick. Yeah, I should be explicit what you don't see here. I have already discarded a lot of things that don't contribute. I have discarded total Q variations, I mean where Q acts on everything inside the angular bracket, and I have also discarded many total derivatives. Yeah. Okay, so this is already good progress. We are down to only 6 different terms, the 3 of them that you see, and another 3 that follow from relabeling. And then, to get to the last line, which is consistent with the overall claim, we do a little bit of integral reduction. We throw away things like that because they are total derivatives. Okay? Then, when the dust settles, oops. So, this is a placeholder for many other integral relations that take you down from 6 terms to only 2 terms. And a representative for the independent Kober-Nielsen integrands are this one and that one. Yeah, it's just linear algebra. Take each of the 6 terms and decompose them in a 2-dimensional basis of Kober-Nielsen integrals. I mean, at the 5-point level, this is an old story picture going back to the early 2000s. But now, the non-trivial part is, what is the coefficient of these 2 basis integrals? Now that we are in an integral basis, you can talk about their coefficients in a meaningful way. Everybody should arrive at the same result if you did the calculation correctly. So you will arrive at some combinations of these V's. And for that combination, you can compute the BRST variation using the above rules. And you find, to your surprise, you will have BRST invariant combinations of triple V's. And the pole structure of this BRST invariant combination is precisely that of the 5-point function. So even before evaluating any lambda cube theta 5 integrals, by just poking at with the pole structure, you can see that you're on the right track, that the expression here must be the color-ordered 5-point function of super Young-Mills. Yeah? So you will produce terms of the form VVV divided by S times S. So this means you are looking at cubic diagrams with 2 propagators. And of course, there may be situations where one of the propagators is cancelled by some k.k upstairs. So there is a 4-point vertex hidden in here. But if everything is gauge invariant, who cares what the 4-point vertex is in comparison to the cubic vertex? It is the one and only 5-point color-ordered Young-Mills tree. Right, and this trick more or less goes through to endpoints. I guess I should better stop here. Yeah, sorry for hopelessly going over time, and thanks. Mm.